Alright, welcome back again, class. Today we will be looking at this series right here, and we'll be evaluating it very precisely. So, the way that a normal mathematician, professional mathematician, will go about solving this, begin by writing out terms. So, we can start by equals 1 plus 2 plus 3 plus 4 plus 37 plus 38 plus 39 plus 40 plus 61 plus, of course, 62 plus 63 plus infinity minus 3 plus infinity minus 2 plus infinity minus 1 plus infinity equals. Now, can any of you students tell me the answer to this? Doesn't it diverge? Get out. Alright, so I want to start by mentioning that the way I'm going to do my videos is I'm going to have multiple series going at a time. Like we have the air resistance series, which will actually be pretty short, only 2 or 3 videos, maybe 4. I'm going to start this series with the series and integrals and fun stuff like that, and that may just kind of go on indefinitely because there are a lot of those. And if anyone does have suggestions for series like this, or just individual videos they want me to make, or anything really, then they can let me know either in comments, or if you know me, then let me know through any other medium that exists. Okay, cool, yeah, good talk. So for this, I'd like to start by saying this does not equal negative 1/12. I know you're all sad to hear that. So we will actually briefly talk about why that is a widely believed thing, though, and why it's not true. And then we'll move on to some other cool stuff that'll serve as bases for future videos with series and integrals and stuff that'll allow us to do lots of cool things that you don't really learn about in high school math. So, to begin with this, there was an Indian in the early 1900s named Srinivasa Ramanujan, who is basically like an amazing, godlike genius who did a whole ton of stuff. He got recruited by a British mathematician, G.H. Hardy, I believe, and got brought over to England, where he worked at Cambridge on lots of theorems and things like that. And before he did that, he had a whole book full of just ideas and theorems that he'd written on his own, and one of them said that this is equal to negative 1/12. So we'll go through how he got there and why that's not correct. So he began with a series called Grandy's series, which is denoted G, which is equal to, doesn't really matter, that, N, which is basically just 1 minus 1 plus 1 minus 1 plus 1 minus 1, Just do that forever. So the way he evaluated this was his first mistake that proves that this is not correct, that it's not negative 1/12. He assumed that this is equal to 1/2 because he just assumed that as you kept going, the average value would be 1/2, which sort of makes sense, but not really, because it's always indeterminate. It's either 1 or negative 1. It doesn't converge, doesn't diverge. It's just 1 or negative 1. That's why it's a little bit special, but it's not 1/2. But we're going to stick with the idea that it is to show what its thought process was. So then he looked at another series. I don't think it has a special name as far as I know, but it was or I can just write it like this. It'd be 0 anyway. There we go. So this the way this would work. Wait, no. Yeah, there we go. So it's be 1 minus 2 plus 3 minus 4 plus 5 dot dot dot. And so the way he evaluated this based on his solution for this is he added it to itself, but he did it in such a way that, okay, let me just write these out and I'll show you what I mean. He shifted over the values, so he added plus 1 minus 2 plus 3 minus 4 plus 5 dot dot dot. But he didn't write it like this. He wrote it like this. 1 minus 2 plus 3. So that the way he added, he would add this and this term, this term and this term, this term and this term, because theoretically it would be the same since adding is commutative and associative, so it would work the same way. So he got 1 plus 0 is 1, negative 2 plus 1 is negative 1, 3 plus negative 2 is 1, and then negative 4 plus 3 is negative 1. And he kept doing this, and he realized when you multiply this series by 2, I'll just call this like n, I guess, just to denote it. But when you add it n to itself, you've got Grandy's series equals g. Therefore, 2 times n equals g equals 1/2. Therefore, n equals 1/4. So he deduced this to be 1/4. Yeah. Okay, so he's calculated these two series, which again, I'm saying are not correct. This is divergent, and this is, it's not convergent or divergent. It's just like not a thing, so don't worry about it. But we're going with this to show how he did it. And I'm saying this so many times because I don't want you to get mad at me and say, oh, I did this because I saw it in a YouTube video, and he said this was like a thing, and again, read the liability thing at the beginning. So, his last step to getting this value of that was he took n, because we call this n, that's g. So he took n, 1 minus 2 plus 3 minus 4 plus 5, and he decided he would do the similar thing that he did to find the value of n. He would do something, he would add it to another series similar to that in such a way that he would only change certain terms, since he was believing that he could just go to infinity, it wouldn't make a difference, which is not true because it's not really how calculus works, and infinity doesn't really work like that. So he knew that he would have to start with n, and he knew he wanted to get to this. So he saw that the even term, or not the odd terms are fine. He doesn't need to change those. Positive 3, positive 3, positive 5, positive 5, etc. But he would need to change the even terms. He would need to add 4 here, add 8 here, and presumably continue adding 12 here because you'd have negative 6. You want to get to positive 6. So it's pretty much every integer multiplied by 4. So then he saw this was actually equal to 4 times 1 plus 2 plus 3 dot dot dot. Therefore, if we call this r, for example, so this is equivalent to n plus, remember this is 4r equals r, which led him to believe that n is equal to negative 3r. So r is equal to n over negative 3 equals 1/4 over negative 3 equals negative 1/12. So that's how he came up with a really weird answer. for adding all positive numbers and getting a negative number, which is obviously not true. And we saw why that's not true, because you can't assume that. You can't assume affinity works this way. But this is pretty much just a meme now, so it's funny to know. So if you ever hear it, you think, oh, I saw Tristan's video, and now I know why this is potentially a thing, but it's not potentially a thing. Remember, no liability. I don't want to get sued. So okay, that was kind of fun, but that doesn't really have relevance in anything ever. So yeah. So now we're going to talk about Euler's formula, which it's pronounced Euler, not Euler or something weird. So don't ever say it wrong in my presence. So many of you may have heard of Euler's formula, but you don't know exactly how, or may look just totally weird. But it's actually not complicated if you've taken BC Calc and all the way through sequences and series. So we're going to use just that to derive it, and then in later episodes we'll actually apply it, but we're just going to stick with deriving it for now. So we want to start with Taylor series, or I guess it's just MacLaurin series. Taylor series don't really matter as much in different radii. So we're just going to stick with MacLaurin series. And we're actually going to, in this video, we're also going to go through a few basic MacLaurin series just because they're good to know in series, even though not all of them will be applicable specifically to Euler's formula. We're going to start with the basic one, which is e to the x. Can't even see that on there, can you? E to the x. Actually, come on. We're going to start with the formula for our MacLaurin series, in case you forgot. I don't even know the variable that's used for MacLaurin. Hold on. Okay, and actually change my mind again. We're going to actually just derive the formula for a Taylor series and why it works, and then we'll say, okay, MacLaurin series is a special case. Just because it's cool to know, and you may not have gotten to it this year in BC because coronavirus sucks. So, we start by taking a function, f of x, and we assume through basic calculus common sense that it can be expressed as a power series, which means equals some constant plus another constant times x minus a to the 1 plus another constant times x minus a squared plus dot dot dot. So essentially it can be written as, or it's a limit because we're in calculus now, you can just write infinity and we're not Ramanujan. And yes, I is a variable used in summation. I know some people have told me that it's not, but we're going to use it. So there we go, basic power series. Now if we want to determine exactly what the coefficients are, coefficients, we can simply take the derivative. So if we take f prime of x, we can, since we know that derivatives distribute over addition, I'm not going to write that out, that's pretty basic calculus. So derivative of a constant is 0, plus derivative of this term, that's just a constant, so derivative of this whole thing will end up, so remember we take the exponent down, 1, exponent becomes 0, this just becomes 1, and if we use chain rule, we notice that the derivative of x minus a is just 1, so it doesn't matter, so it ends up being plus c1 plus c, excuse me, that's alright. So then we go into this term, take the exponent down, constant doesn't change, again derivative of the x minus a is 1, so that doesn't matter in chain rule. So 2c2 x minus a to the 1 plus, and the same thing kind of works, 3c to the 3 x minus a squared plus dot dot dot, etc. So then if we're going to do one more derivative just for explanation's sake. F double prime x equals 0. I'm not going to write the zeros this time. 0, 0. This becomes 2c, 2 3c2 plus 6 now, c3x minus a plus, this will end up being, the original exponent on the next term was 4, and so, and this current exponent, which we're also going to take the derivative of, is 3, so 4 times 3 is 12. 12 c4x minus a squared. So we can start to see a pattern here, and if we plug in, the basic way to derive a Taylor series is if we plug in f of a at any specific derivative, then we're going to notice, like if we plug it in here, f of a, this term will become 0, so this term, we'll just use a different color. So if we plug in a, right, this becomes 0. Bam. This becomes 0. Bam. Only thing that's going to be left is that, which means that this constant, we'll write these down here, c0 equals f of a. Now if we do the same thing for f prime, plug in a, 0 is nothing. This stays, 0, gone. Oh yeah, you're right, 0 is like that. 0, gone. So again, we can see this is the only term left. So c sub 1 equals f prime of a. Okay, so now when we do go on to f double prime, plug in a, the same thing happens, that cancels, and we're left with 2c this time. Now, maybe thinking 2, or we can go ahead and c sub 2 equals f double prime a over 2. And when we take the third derivative, we're going to have another coefficient. The coefficient of c3 is going to end up being 6. And so this term will be c3 is equal to f triple prime of a over 6. And if you think about it, the process that, say, like that 17th term is going to have to, 17th term in the original function is going to have to go through to become the constant term. It's going to have to take, you're going to have to take the derivative 17 times, which means you're going to bring the exponent down and multiply it every time. So you're going to bring down 17, multiply it by 17, then 16, then 15, then 14. And if you notice, that is going to be 17 factorial. And if we notice here, we're going with 0 factorial is 1, because that's like generally accepted. There's not really a reason, it just kind of is, because it works for everything. Then 1 factorial is 1, 2 factorial is 2, remember. And 3 factorial for the third derivative will be 6. And then 4 factorial is 24, and that'll be 12 times 2 times 1, which is 24. So we can write a general formula for c sub n equals f, the nth derivative, in case you're not familiar with that notation, at a over n factorial. Okay? So now we can write a whole formula for a Taylor series. Okay, I went ahead and wrote the definitions on the corner just so we have them. So we're going to start with the most basic function in calculus, which is f of x equals e to the x. And it's the simplest thing to find a MacLaurin or Taylor series for, because it has the special property of that for any nth derivative of, like a natural number derivative, an integer, positive integer derivative of e to the x is e to the x. So that's cool. So we have that. So if we want to write it as a Taylor series, or a MacLaurin series, e to the x equals and f of 0 will always be e to the 0, which is 1. So that'll always be 1. So we'll have, not e, okay. So this will always be 1, so we can pretty much just remove this from the whole equation. So it's x to the I over I factorial. So there you go. It's very simple. And if we want to write that out to see what it looks like, it'll end up being 1 plus x squared over 2 plus x cubed over 6. Or maybe nicer to write it like this. So that's very helpful to know. Alright, what's another easy thing to think about? We could do sine of x, because that also has an interesting derivative property, if you recall. So if f of x equals sine x, then f prime of x equals cosine. What the hell? Cosine x, f double prime equals negative sine x, f triple prime x equals negative cosine x. Then f fourth of x equals sine of x again. So it comes right back around. So if we find the MacLaurin series and we plug in 0 for all these derivatives, well, f of 0, or sine of 0 is 0. Then we get to cosine of 0 is 1, then 0, then negative 1. So we have 0, 1, 0, negative 1, 0, dot, dot, dot. So if we want to write this as a MacLaurin series, we can write m of x equals, first coefficient will be 0. So we're just going to start with x to the 1. So x over 1 factorial. The next term is 0, so then we skip to the x cubed term, but we have to subtract it, x cubed over 3 factorial. And we just keep alternating with all the odd powers. Yeah. Plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Dot, dot, dot. Cool. So, and we can quickly do cosine as well as a similar property. So if we just like get rid of that, and this will become the 0th derivative, that becomes the first derivative, that becomes the second derivative, this becomes the third derivative. So the first term will be 1 because 0th derivative is 1. So 1, then we skip, we're going to start skipping all the odd powers instead of the even powers. So we're going to go over to the second power, second derivative, and that'll be negative. That'll be minus x squared over 2 factorial. Then if we go to the fourth derivative, that'll be positive again, because remember they oscillate back and forth. X to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. That keeps going on. So these are some more common, generic, basic, simple, whatever, MacLaurin series. Okay, this will be the last example, but we will briefly talk about 2 other examples that stem directly from this that are pretty easy to see. So with natural log of 1 plus x, if we plug in 0 up here, we're going to get natural log of 1, which is 0. So f prime of x, okay, so the derivative of the chain rule thing, this chain rule won't matter because the derivative of 1 plus x is just 1. Okay, so derivative of that, remember, derivative of ln x is 1 over x, so this will just be 1 over x plus 1. So if we plug in 0, we just get 1. F double prime x equals, so we're going to treat this as if it's x plus 1 to the negative 1. We're not going to try to use quotient rule since you don't want to do that when there's just a 1 in the numerator. It doesn't matter. So we're going to treat this as if it's x plus 1 to the negative 1. So we bring down the exponent, which is negative 1, and we lower the exponent to negative 2. So we're going to end up with negative 1 over x plus 1 squared, since this is the same as negative x plus 1 to the negative 2. Yeah, so if we plug in 0 here, we get negative 1. Now, third derivative, do the same process, bring down negative 2. Negative 1 times negative 2 is 2, and lower the exponent. In this case, we can think of it as just increasing the magnitude of the exponent. So we have this, and then this term will be 2. And then f fourth x will be, again, we bring down this exponent, we get negative 6, because 2 times negative 3, over x plus 1 fourth, and we get negative 6. So you may be starting to see the pattern here. It is, this first term doesn't really count for anything. We're going to kind of ignore it because it's kind of stupid. But you can see these are factorials because, again, we're doing the same thing we were before, which is repeated differentiation, because we're bringing down consecutive exponents, which is going to give us a factorial. So this is 0 factorial, actually. This is 1 factorial, this is 2 factorial, this is 3 factorial. And since we're using a negative exponent, the sign's also switching. So we want to add negative 1 to the 0, negative 1 to the 1, negative 1 to 2, negative 1 cubed. This gives us the easy formula of fn of x is equal to, now remember this term doesn't really make sense in the series, and we're going to talk about why that's helpful. Or not the series, the pattern, I guess. We're going to talk about that in a minute. So where it actually begins, when we want n to be 0. So when n is equal to 1, we want this to be 0. So n minus 1 factorial times negative 1 n minus 1. Yeah, so for all, no, we don't write for all like that. We're math pros, so we write the upside down capital A, because that means for all. If you didn't notice that earlier when I used it, that's fine. So for all n belong to natural numbers greater than 0. I actually don't know if 0 is a natural number, but we're just doing natural numbers aren't 0 just in case. So you get the idea. So what this means when we plug it into a MacLaurin series. So m of x is going to equal limit as n approaches infinity sum to n of 1. We're going to start at 0 again. This means that, and again, we're shifting all derivatives and things like that. So the ith derivative, we don't, excuse me, we actually want to start at 1, because 0th derivative doesn't make sense in the pattern because it's just going to be 0. So we start at 1, and when we have the first derivative, then we plug in I minus 1 factorial times negative 1 to the I minus 1. Remember, we divide that by I factorial times x. Now, what do we do for x? Well, remember, we don't want to change the pattern of a MacLaurin series. We just have a different pattern with derivatives. So we're going to keep x as to the I power, because if x were to the 0 power, then that still wouldn't count. So if we write this out, and first, sorry, getting ahead of myself. We have to see that I minus 1 factorial over I factorial actually cancels out to just 1 over I, because, yeah, that's this. So we can rewrite this as negative 1 to the I minus 1 times x to the I over I. This is kind of cool looking. So that'll end up looking like x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Right? So, there we go. So what else can we do with this? we have this series. This series is down. But like I said, we're going to stem two other things off of it. So the first one is, we notice that 1 over x plus 1, that's a pretty common thing too. So if we just take the derivative of this whole series, which is the same as this, then we're going to get f prime of x, which is this. We can just find the MacLaurin series immediately for 1 over x plus 1. So m prime of x, and we don't want to, we could do it with this, but that's kind of annoying. Actually, we can do it with that. Let's do it over here. So take derivative of that, we're going to get 1. Take derivative of this, we're going to cancel out the 2 that we bring down and the 2 that's already in the denominator. We're just going to get x. And same thing here, we're just going to get x squared, then x cubed. And so we're going to end up with 1 minus x plus x squared minus x to the 4th. It's just going to keep going like that, is equal to, keep forgetting the limit. I've been doing too much non-calculus stuff. And we can go back to using 0 because the first term does actually exist. So we don't even need to use like a formal notation for MacLaurin series. We can just do it based on this. That's pretty easy to write in sigma notation. Negative 1 to the I times x to the I. So there we go. Equals 1 over x plus 1. Right? Okay, so the last thing we can do before we finally move on from all these MacLaurin series is we can think of the function f of x equals 1 over 1 minus x, which is also commonly used. And this is very closely related to 1 over 1 plus x because we're just adding a negative to this, which, if you remember, when we were back here, we noted that the chain rule doesn't matter because the derivative of 1 plus x is just 1. But now, it's the same thing as this, but the derivative of 1 minus x is negative 1. So if we have, back up. This means that for every term that we have, we're going to have to multiply by the chain rule, which means that we're just going to pretty much multiply by negative 1 to the I again, which will just cancel out this, because if we do that, here I'll write it out. If we do this, this is just going to end up as negative 1 to the 2i, and negative 1 to the 2i is the same as negative 1 squared to the I, which is 1 to the I, which is always 1. So there we go. So we can just remove that whole term, and we just get x to the I. So that'll just be 1 plus x squared plus x cubed plus x to the 4th. Okay, so that's our last cool MacLaurin series. Now we're going to finally go on to Euler's formula. Also, sorry, I just realized you couldn't see this, but I wasn't really writing much down here. I mean, you know the chain rule will give you, I think you can do negative 1 to the I, negative 1 to the I equals negative 1 to the 2I by yourself. So okay, so notice I didn't write them over here this time because we're not going to be using them in the derivation of Euler's formula. But if you are like serious about studying this stuff, which I hope you are because it is interesting, it's fun, and it'll pay off, especially if you haven't taken calculus yet like me. It's good to write them down and just keep them in the back of your head because they're really good for memorizing, as you'll see in the next few episodes of this series. And if you do have the Stewart calculus textbook, which is what I'm using, I don't know what version you have, but in their sequences and series chapter, they do have a table of MacLaurin series that are easy to remember. And pretty much all the ones I said, plus 2 more, inverse tangent, and just binomial formula. And binomial formula, if you probably already knew what that is, but it was actually first determined by Newton as a MacLaurin series, so that's interesting. Okay, so Euler's formula. I'm not going to explicitly say what it is if you don't already know what it is. We're just going to get to it and you'll be surprised. And it's pretty cool once we get there. So to do this, we need to make a few observations. And to do that, we will need to use e to the x, sine x, and cosine x. That's why I've left these here and I didn't write the rest of them. So if we look at e to the x, let's just theoretically think about what would happen if we wrote e to the ix, where I equals the square root of -1. If we plug that into here, then what? So this is essentially x to the 0, and I to the 0 is 0, or is 1. So we still have that term. Then we have xi. We're going to write the i's out to the side so we can differentiate between the imaginary terms and the real terms. So we still have x over 1 factorial times I. But then the next term we have x squared, and I squared, as you can see from this, is -1. So we subtract x squared over 2 factorial. But this is a real term because I squared is -1, and that's a real number. And then I cubed, or we can just write a basic formula. So I to the 1 equals I squared equals -1, I cubed equals -1 times I, which is just I to the 4th. You can think of it as -I times I, or as I squared, which is -1 squared, which is 1. And then I to the 5th is just 1 times I, we get back to I again. So it cycles through like this, kind of like how the derivatives of cosine and sine do. But here we go. So when we get to x cubed, we see I cubed is -I, so we're still subtracting x cubed over 3 factorial times I, and we'll do a few more terms. X to the 4th over 4 factorial, because I to the 4th is just 1, plus x to the 5th, x to the 5th over 5 factorial times I. That's actually negative. We'll cut it off there, and now we're going to erase this, and we're going to split it up into the real and the imaginary terms. So the real terms are 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. If you're starting to get it, then that's good, we'll get there. Plus, now the imaginary terms. I'm just going to factor out all the i's just to make it more concise. So I times x over 1 factorial minus x cubed over 3 factorial. Wait, I did this wrong. Haha. So if you're yelling at me, telling me, haha, Tristan, no, thank you. X squared over 2 factorial plus x to the 4th over 4 factorial, whatever, plus I x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial, Now, what do we notice? This is the same as this. It's kind of interesting. Cosine x. And this is the same as this. Plus I sine x. There you go. That's pretty cool right there. It's hard to imagine that that can actually be a thing, because if we think about this on the complex plane, then you probably have seen this if you even just taking pre-calculus, cosine x plus I sine x. I think they called it like cis x or something. So essentially, x is an angle, because if you plug in, say, 0, then you're going to get this is 1 and this is 0, so you're going to end up right here. But if you plug in pi over 2, this is going to be 0, this is going to be 1, going to end up here, and so on. So it's basically a different way of writing polar coordinates almost, or yeah, pretty much polar coordinates. So essentially, it's often written as e to the I theta instead, because it is seen as an angle. So cosine theta plus I sine theta. So yeah, if you're in Miss Poole's pre-calc class this past year or the year before that, and you haven't seen this, then you're probably jumping out of your seat because it's pretty cool. So Euler's actual formula is, if you plug in theta is equal to pi, e to the I pi will be equal to cosine pi is -1 plus sine pi is 0. So this leads us to, can you even see this? Yeah, you can. Okay. E to the I pi plus 1 is equal to 0. So that right there is Euler's formula. Take a minute to appreciate that. This is, if you're aware of who Richard Feynman is, he's a physicist from the 20th century, and I think he only died the past few years. I'm not exactly sure. But he's pretty recent. He was somewhat of a physics and mathematics prodigy. Well, if he was a physics genius, then yeah. When he was 15, I think, he wrote in his personal notebook that this is the most beautiful formula in all of mathematics, because it encompasses 2 transcendental numbers, a complex number, and 1 and 0, and it's just, it ties together so much mathematics that you wouldn't think would be related. How could E, which is related to calculus, and it's defined in a totally different way, sometimes with economics, sometimes with derivatives, it can still be related to simple circles and trigonometry and pi, and it's connected through a number that isn't even real, technically. The square root of -1 isn't a real number. And it gives you a negative value. An exponent gives you a negative value. So it's just surreal to think about. So that's all I'm going to talk about today. We'll talk about other stuff with this in the future and stuff it can be used for. But I just want you to appreciate that as much as I do. And if you are interested in it, you can, I think I've already mentioned this book, but this book, a lot of it is pretty advanced stuff, but it has tons of applications of complex numbers and this formula right here, and it's obviously named after the formula, so I would recommend it if you are interested in this. And some of the stuff I am going to talk about in this series is pulled from this book, and it's just amazing, so I'd recommend it. So I guess that's it, and I will see you soon for some more air resistance.